So previously we kind of dealt with vertical expansion. So if we had something like this, f of, 3x squared, we know that that's a vertical expansion, and we know that that doesn't really affect differentiation. So we just factored that in after the fact, and we basically just said, okay, well, we're just going to keep that as 3, and we know it's vertical expansion and affects the derivative by 3 times. But what about these horizontal factors? Okay, so this is a horizontal compression. If we look at the horizontal compression factor A, what does it do to the slope? Okay, and how does it affect the slope graph? Okay, so here is my sine function, and I compress it by 3 times. Okay, if I compress this function by 3 times, what's going to happen to its derivative? So what do you notice about the different parts of the graph? So think of that part going through there. That same slope section, so there's my different color here. So you can see that slope section and that slope section, that one looks a bit steeper. So it looks like that horizontal compression is actually making the slope steeper. So this is my regular slope, horizontally compress it, it looks steeper. In fact, it is. And so if we take a look at a triangle, there's my slope triangle. I'm going to take this slope triangle and I'm going to horizontally compress it. What's happening to the run? Well, if I compress the run by half, I get the same rise, I got half the run, I have twice the slope. It's twice as steep. Okay, so and the reverse happens if I horizontally expand it by 2. We'll have double the run, so we'll have double the number in the denominator. I'm going to have half the slope. So that compression factor is going to inversely affect the slope. Okay, or sorry, it's going to directly affect the slope. So a compression of 2 makes it twice as steep. So that's what's happening here. This compression of 3 has made these slope sections, so again, this slope section compared to this slope section, it's made it 3 times steeper. So we count for that by doing this. So when I differentiate, my derivative of sine normally is cos, but I'm going to account for that extra 3 with a times 3 on the slope. And that makes the slope of every point on that cosine graph 3 times steeper than it normally would have been because of that horizontal compression. Now, we will deal with that a little bit slightly differently once we learn another rule called the chain rule, because the chain rule then will account for this. But for now, anytime we see a horizontal compression, we're going to have to remember to times by that compression factor to get the steeper slope values or bigger slope values. So in general then, when I have the derivative of a horizontal compression, I have to differentiate and add that extra times A. So if I take a look at this graph here, if I differentiate this, so y prime, the derivative of log is going to be 1 over 4x. Okay, and then because it's horizontally compressed by 4, I have to times by 4. And oh, look what happens. These cancel out. So I end up with a slope function as 1 over x. That's strange. If you recall from the logs though, the reason why this happens, we can actually justify why this horizontal compression just seems to cancel out. It's because of this. If we use some log properties, we can actually split off that log property first, and then as we differentiate it, that's going to differentiate to 1 over x. That's going to differentiate to 0. So that actually times for compression could have been shown as a vertical shift, which then doesn't affect our slope whatsoever. Okay, although it changes the graph, that horizontal compression really isn't a horizontal compression. In some ways, we can look at that as a vertical shift. Okay, but we applied the rule correctly, and we got a result that is consistent. So what about horizontal shifts? Well, if you take a look at this horizontal shift from x squared to shift it to the 3 to the right, the shape of the graph doesn't really change. What's happening? Well, that slope function, instead of having a slope of 0 here, now the slope of 0 has been shifted over, but everything else remains the same. So that horizontal compression factor really, if we can recognize it as horizontal compression, we just leave it alone. All we're going to do is differentiate the power to power 2. As long as we keep the same relative horizontal compression, it has no effect on the derivative. So horizontal compressions, for now we're going to deal with an extra times by that compression factor because it affects the slope. And horizontal shift, we're not going to do anything because that horizontal shift has no effect on the derivative other than we have to make sure that we keep that shift in our derivative. Okay? So this example here, that all that is a horizontal shift. So when I differentiate this, I keep the 2. I'm going to differentiate the secant, the tan into secant squared. And as long as I just keep it in the same relative position, that's all I need to do. There's nothing that affects the shape of this graph, so I don't need to do anything with the minus pi shift.